G'day. It's me again, your serial pest. We've got our last unit, all about ecosystems, which hopefully will mean we'll get into the reserve and do some ecosystem study, um, depending on whether we have exams or not. Not too sure what's happening at the end of term yet. However, fortunately, those of you who had me last year, well, we did this last year, and there's a chance to build on that. Those who had Mr. Benton, I think, still did this last year. So we should be building on knowledge rather than necessarily starting from scratch. Let's see how we go. As always, it's biology. There's lots of new words to worry about. So ecosystems are a combination of abiotic and biotic factors. And importantly, an ecosystem is something that exists in a particular space at a particular time. So the spatial and temporal dimension to these. There's some nice new words for you too that you can put in your vocab. So what does that mean? Well, the organisms are our living things. So we're talking about, sorry, let me move around, talking about plants and animals and bacteria and fungi, all those things that exist in an environment that are alive or have been alive. That's important. So dead living things, ex-living things, are still considered biotic. And then the physical environment, the water, the air, the soil, these things are considered abiotic. And so we talk about the biosphere, where we live, the living things exist, overlaying the interaction between the atmosphere, the air, the hydrosphere, the water, and the lithosphere, the soil and rock. And so we live in that interaction, that space where all that interacts. And of course, all these things influence each other. So ecosystem studies are about the study of interactions and how they change if things occur. So of course, it's the classic old food chains and food webs, which you're well and truly aware of by now, I'm sure. So the food chain, sorry, simply, we've got a little flowering plant here. Here's our autotroph, transforming energy from the sun into chemical energy. The butterfly visits and takes some of that energy with it. It gets eaten by a frog, passes the energy onto the frog gets eaten by a snake, passing its energy to the snake, and the snake gets eaten by the hawk, or eagle in this case. The eagle gets to have the last bite and gets that energy passed onto it as well. There's another stage, of course. They get decomposed. So the decomposers are the last stage, returning organic material to the soil. We'll talk about them soon. And the food web then just shows how much more complex it is. And so now we've got 4 producers for these autotrophs being consumed, the first order of consumers, a second order of consumers, a third order of consumers, and then finally we've got our apex predator. And there's not too many. As we work up through here, we lose numbers of individuals because the energy is lost. There's a lot of very inefficient system. So we talk about trophic levels. And so producers are the autotrophs. That's a trophic level. And so in the vast majority of ecosystems, we're talking about plants, of course. And they trap the sun's energy, and they convert that sunlight energy into chemical stored energy in the form of glucose, which they'll store as starch and cellulose and other complex carbohydrates. And then, of course, we'll eat that. And the plant also is storing it for its own purposes, so it will also destroy that, or not destroy, convert that chemical stored energy into ATP, active stored energy. So it's all that photosynthesis, respiration stuff we've done earlier. We also find there are some ecosystems on the planet which live in deep oceans where they don't get light, but they rely on the energy, the heat energy, and the chemical energy that comes from volcanic eruptions in those deep ocean trenches. And so we have a whole lot of bacteria at the base of quite complex and strange looking food webs in those deep ocean trenches and in deep oceans in general. But they're also converting energy into a form of glucose that can be used. So they're the autotrophs. We, of course, belong to this group. We got the heterotrophs. And as you work up from producers to that first order consumer, which I am, I'm a first order consumer. I'm a vegetarian, so I don't eat animal flesh. We get our energy from eating plants. And so the energy the plant has created is the wrong word again, has transformed from the sun into glucose forms our basis of our energy sources. Herbivores get eaten, of course, by other consumers. And so those consumers are what we often call omnivores. And they eat plant and animal material, gain their energy from that purpose, from the process. And then the highest order of consumer, and it's not normally more than 5 layers, is the carnivores, the apex predators, which generally just don't eat anything but meat. And there are generally a few of those in the environment. We're one of those weird individuals, because of our brain and the way we've evolved and we've taken charge of the ecosystem. We have certainly become the apex predator in most situations. Although go swimming in the ocean with sharks and you suddenly become a second or third order consumer, or go playing with lions in the savannah, things can change. But generally, we are apex predators just by the nature of the way we interact with the environment. And then, of course, there are 2 really important groups that we often forget about, and these are our decomposers and detritivores. And essentially, they're the things that break down dead matter, old living things, and return the organic material that's bound up in them to the soil. So without them, our systems would run out of organic matter to maintain it. The plants can keep making more, creating more glucose for us. Watch those words, but they would run out of organic matter eventually if these decomposers and detritivores weren't working. I won't go into the difference between this. That's important. We also have to look at the interactions between these organisms. So we're well aware of things like predator-prey. So one animal hunts and eats the other. But there's also what we call symbiotic relationships, where animals and plants, or particularly animals, live in common interaction with each other. And in the case of mutualism, we have a situation where both these animals have benefited from their interaction. On the case of lichen, lichens are organism made up of fungi and algae, and they both benefit from that interaction, so that this thing exists in its own sense. Commensalism is where one is benefited but the other isn't harmed. And of course, in a parasite-host situation, it's a bit more like the predator-prey, where the parasite tends to eventually damage the host so badly that it dies. Not a good outcome, really, for the parasite in many ways. So these are what we call the biotic factors. And then the abiotic factors are all about the energy movement. So energy is abiotic. Water, everything needs water. Maintaining a reasonable temperature fluctuation through the day and through the year, because most things don't like it too hot or too cold. And then the substrate, that soil everything grows in. Which we'll look at now. Where am I? That button. So energy obviously is the majority of energy in our ecosystems is from the sun. There are some cases where we get geothermal energy forming parts of the basis, and obviously some chemical sources, so those volcanic activities will lead to energy into those situations. But essentially we're looking at photosynthesis. So it's sunlight energy being converted to stored chemical energy in the form of glucose, and that glucose being converted into a form of chemical energy we can use in the sense of adenosine triphosphate, ATP. We refer to that the ability of an ecosystem to create that energy to support it as its primary productivity. I'm struggling this morning, aren't I? And then the amount of energy stored is called its biomass. So what's available to that ecosystem. These are extra terms that we didn't talk about last year. But it is incredibly inefficient. So if we consider 100 lumens or whatever as the amount of energy that arrives every day, 99 of them go back out into space. Only 1% of that incoming solar radiation is actually converted to glucose in our systems. Most of it's lost. So straight away it's inefficient from the very first step. That's why we need many more plants than we need animals, because the plants then support all those animals above them. And then at each level, we see more energy loss. Generally it's heat. So this is a little biomass pyramid. So here's the biomass of the producers. Huge, as it should be. That first order consumer, much reduced in comparison, about a third. Then again, another third in the second order consumer. And then look at that sparrowhawk living on that system. We might have 2 or 3 who can live in that small space. So we often find we've got a pair of powerful owls working in Langwarrin at the moment. There's only a pair. Many more than that wouldn't cope, especially with the amount of other raptors we have in the area. So you can only carry so many because the energy doesn't exist. A variation of this is bioaccumulation, this idea of the effect of pollution. So in this particular diagram here, we've got effluent entering from this factory. Here's the water here, and it's coming in at 0.01 parts per thousand, which is not particularly significant. And the plankton will, pick that up through being in the water, and they start to accumulate in their flesh, and we're up to 1 part per thousand. So it's still probably not that big of a difference for the plankton. The sculpin are these little fish that eat the plankton, and in their flesh we start to find 20 parts per thousand. So they're accumulating this effluent, this chemical that's come from here. In this case, we're looking at a thing called TCDD. And then, of course, we have this fish-eating bird, this egret, who's going around. He's having a lovely time eating a sculpin, but now we're up to 50 parts per thousand. So it's probably becoming quite significant for this bird. And then, of course, the bald eagle will take out this egret here, and all of a sudden we've got 110 parts per thousand of this TCDD in our bald eagle. And the consequences are then felt. This was seen in the 60s and 70s, and Rachel Carson was a particularly influential person in this area, talking about how this accumulation was killing off the bald eagle and falcons and other hawks. The mothers would sit on the eggs and crush the eggs. It was actually affecting their ability to make a strong egg. So the consequences are often quite strange. I'm running out of time, so I won't go into too many of those. The other really important thing, of course, is the cycling of nutrients. Now, I've included water here, although it's not necessarily a nutrient, but we need water, we need carbon, we need nitrogen, we need phosphorus, we need sulfur, yada, yada, yada. And they all cycle through the biosphere and its interactions with the lithosphere, atmosphere, and hydrosphere. So, of course, water is all hydrosphere. So rain falls, there's all snow, and it precipitates down, runs down through systems, gets into the groundwater, so the lithosphere gets water in it, comes out into oceans, evaporates, and this goes round and round and round. And of course the biosphere is in here. We're using that water on its way through. So water is important for us. That cycle is really important to keep occurring. The carbon cycle is the same. The carbon's a bit more complex. And again, we've got plenty of carbon in the atmosphere, plenty of carbon tucked away in the soil, plenty of carbon dissolved in water, and then all these things that live on that process are carbon-based. We're all carbon-based life forms. We need carbon. And so that carbon cycle is really important to be kept in balance for us, which concerns scientists at the moment because it's out of balance. We've got too much carbon in here and not enough in here and in the plants. People talk about storing stuff from the atmosphere into the soil, which would work if we can make it work, but it's a new idea that's in process. And then nitrogen does the same sort of thing, and it gets bound up in plants and stuff in the soil. And most of the nitrogen on the planet's actually in the atmosphere, which is no use to us. We need it bound up into our plants so we can eat it. And I'm running out of time, so I'll go stop there because I'm about to kill my 15 minutes. So we'll look at those in more detail in our style lessons. But fortunately, we can do them face-to-face now, and I can be there and we can talk about it and help, and won't be quite so daunting. So I'll see you in class very soon.